lecture. We are quite happy that we could have Professor Graeme Segal from Oxford here to deliver these lectures, 6 lectures, Monday, Wednesday, Monday, Wednesday, Monday, Wednesday, in this room, with the exception of one Wednesday next week, and it will be held in the regular class in the Kleinberg Hall. We get these technical things in the beginning, and before we start, let me introduce our speaker. Graeme Segal was born in 1941 in Sydney. Then he started at the University of Sydney, bachelor studies, and he moved in 1962, first for a year to Cambridge, and was a student at college, and then he changed to Oxford. The current student of Michael Attier. His PhD was in 1966, but already in 1964 he was visiting Bonn for the first time, so in 3 years we will re-invite him for the 50th anniversary of this first visit to Bonn. And then was research fellow, lecturer and reader and professor in Oxford, then moved to Cambridge for about 10 years to succeed Frank Adams, professor of mathematics. Then he went back to Oxford and was a fellow of All Souls College and retired in 2009. He is, of course, a topologist well known for his work on K-theory and index theory, then on homotopy theory, loop spaces, and formats. There is a well-known book on loop groups, and then he is one of the founding fathers of topological field theory, the topic he has chosen for this lecture series. He's also well known as, since he has been for a long time editor of topology, and is the founding editor of the new journal of topology. So the lecture series has the topic 3 roles of field theory. Welcome, Professor.
Well, thank you, Carl Friedrich, for that very kind introduction. I feel very honoured to be asked to give these lectures. I feel great affection for Bonn. As Carl Friedrich said, Bonn was the first foreign place I ever came to, apart from family holidays. I came here in 1964 when I was a graduate student. I was sent, as it were, by my supervisor, Michael Attier, to visit Algebraic. And as I walked down the Poppelsdorfer Allee today, it was a very familiar feeling. Although I must say memory is a very deceptive thing. I have the map, the street map of Bonn, which I bought when I came here in 1964. And despite that Bonn seems exactly the same to me, the centre of Bonn is sufficiently changed that this street map is completely useless. I'm afraid I'm going to begin with a sad thing. Some of you probably know that my colleague Dan Quillen died on Saturday. He was, of course, a great mathematician, and a great loss to the world. He was one of the first people who taught me about quantum field theory, and I've learned an enormous amount from him, a lot of which is going to be in these lectures that I'm going to be giving here. 25 years ago, the two of us, he was a close friend, the two of us formed a plan to write an account together of quantum field theory. Our ways, our styles of existence were so hopelessly different that was never really likely to happen. But we spent endless time talking about the subject, and a lot of that will be reflected in my lectures. So in that sense, it's a very sad moment. So I'm going to talk today, in particular, in very general terms about the sort of thing that quantum field theory is. So let's begin right at the beginning with classical physics. I mean, physics in the year 1900. So how did that what way did that describe the world? I think it's important to begin with this question in order to see what quantum field theory is trying to do. But by the way, am I audible? Please put up your hand if you can't hear me. I don't have to choose which blackboard to write on. It seems very discriminatory. Try not always to write on the same blackboard. So anyway, let's begin with this is going to be blackboard, not like a German blackboard where you have to press buttons. So let's talk about physics in 1900. So how did it describe the world? Well, you see, the first thing it did was it assumed that we know about space and time about time and space in advance before we start even talking about physics. So in particular, well, we can assume that time is some one-dimensional manifold. We think of like the real numbers, and this will be some three-dimensional Riemannian manifold in classical physics. And then the next move of classical physics is ontology. So you see, we have something which is really a kind of functor, that given space and time, physics tells us what the world consists of. And classically, of course, it said the world consisted of particles, point particles, which interacted by means of fields. So the first thing it did was it gave us some ontology, you might say, which is really, if you like, a functor in one word, which gives us some new manifold x sub m, which is the configurations of the world at a given time. At some time, let's say t. And what would this be? Well, a point of this would be some infinite dimensional manifold, and a point of it would be, then a point of this manifold would be a collection of points of this one, the positions of the particles. Maybe there were different kinds of particles, and you'd have several different subsets. And in addition, you'd have the fields, which roughly speaking would be some kind of functions defined on M, which would record the way things interacted. So I want to just think of that in very general terms. Well then, so that was the ontology, and then what was the physics? So the physics really consisted of three statements. It said that the actual state of the world was determined by this configuration with its time rate of change. So the state of the world was determined by a tangent vector. So that was the first statement. When you knew the state, you were meant to be able to know how the world evolved. And that evolved in a very simple way. First of all, it had a symplectic structure. There was a Poisson bracket on its functions, or a closed two-form. There was a symplectic structure. And there was a function, so-called Hamiltonian function, h, which told you all about the evolution. It tells you that the way, let's call this point this ym, the manifold of states. It says that if you take a point in here, the way it changes is such that if you evaluate the symplectic form on this and another vector, that's just the gradient of the function h in the direction eta. This is, of course, called Hamilton's equation. So that's a very simple picture. But what I want to emphasize is that it proceeds in two steps. On this side, you have something that you might call a classical dynamical system. So a classical dynamical system for this purpose is a symplectic manifold with a function. And the state is a point of it. Apart from that, however, because that doesn't give you any kind of description of the world, the description of the world is really encoded in this functor, which tells you that given space, we know how to construct this manifold. Now, roughly speaking, what quantum field theory is trying to do is it replaces this classical system by a quantum system, and then the important thing is it gives you a functor from manifolds to such systems, which is meant to be the analogue of saying the world consists of fields and particles. Well, even before coming to quantum theory, let me just point out in a couple of words what goes wrong with this picture. Why did we ever need to go beyond classical physics? Well, in fact, it was 1900 is a very kind of crucial date. If one had moved a little bit either way, the picture would have been rather different. For example, why did one need fields? The fields certainly make things very complicated. But you see, already before 1900, Maxwell's equations had made people aware that electromagnetic interactions between particles don't happen instantaneously. When one electron acts electrostatically, so to speak, on another electron, the effect is only transmitted at the speed of light. So if you want to be able to say what the state of the world is at a given time and work out what it's going to be, then you need to have some information not just about where things are, but where they used to be in the past. And what the fields do is encode that. Because there are other mathematical reasons why you might like the fields, but basically, once you have the beginnings of relativity, the fact that things only move with the speed of light, then you have to have fields. On the other hand, once you have fields, you are kind of on the road to the whole thing blowing up. Because, you see, what is this field? The field generated by some charges, which are more or less attracting each other by inverse square law or something, that's just some function. It isn't that each particle generates a field which acts on the other particle. There's just meant to be one field through which all the particles swim. And obviously the field is going to be infinite at precisely the points, the positions of the particles where you need to know what it is. So if you really want to have point particles, you're pretty much doomed from the start of the classical picture. People tried to imagine that things like electrons were extended bodies, but that never really worked. So there are already problems. And in some sense, quantum field theory can solve it. Well, so first of all, what, roughly speaking, is a quantum system? So the quantum system, so we'll forget about the ontology. What do we do with this symplectic manifold? So a quantum system is easy. Well, it's a star algebra, topological. So it's an algebra over the complex numbers. And it has some, it's not necessarily commutative, it has some anti-involution, which is complex antilinear called star, and it has a topology with respect to which its multiplication is continuous. Now, in this lecture, everything is going to be on a level of great vagueness and so on, so I don't want to get too involved in what kind of topological star algebra and so on. And so this, and we have also a linear form positive linear form. The linear map, it's a star map, that means a complex conjugate of this, and it takes things in the form of A star A to positive numbers. So this is a quantum system, and that's meant to be the thing that takes the place of the symplectic manifold and the point of the symplectic manifold. So this linear form you traditionally call a state. Now, some of you may not particularly like that description of a quantum system. It might be more familiar, possibly, to say that you have a Hilbert space, and the states of the system are the rays in this Hilbert space, and the things you measure, the observables, are self-adjoint operators in this H. So you think of A as being operators in some Hilbert space, and you think of this linear form when you have a ray, a line L contained in that. You can pick a vector, say a unit vector in that, and then we would, thinking of A as an operator, this would be the inner product of psi A psi. I don't particularly like this description. I feel that this description, well, certainly for my purposes, this is the description you want. It's somewhat more general. You can roughly, in some sense, you can go backwards and forwards between the two. But this is a sort of, I always feel this is a creepy, dishonest kind of description, because there's no information. A Hilbert space with a vector in it is completely information free. They're all the same. So if you want to say a quantum system is that, then in some sense there's only one of them. But we can say a bit more, which slightly goes against, I'm going to abandon this anyway. This statement is meant to carry over, in that there's meant to be an element in here, a self-adjoint element called the Hamiltonian, and the analog of this equation tells you about time evolution. So this thing, this algebra, it evolves by a one-parameter group of star algebra automorphisms, and the way in which an element of it changes corresponding to that. So the rate of change of this is essentially the commutator of this and this of I. So that's Planck's constant. So this is the analog of that equation, and the Hamiltonian function becomes the element of the algebra. Now, so what is the relationship between this and this? I mean, in what sense is this meant to be an improvement and this? How does one compare them? Well, you see, the idea is meant to be that when you have a quantum system, it's a nasty non-commutative algebra, but somehow you're not interested in all the things in the world, you're just interested in some things that you're observing, and you somehow manage to fix inside this algebra some smaller thing, which for your purposes you can think of as pretty close to being a commutative algebra. It's a commutative algebra which is a little bit deformed away from commutativity. Well, so a commutative algebra looks like the functions on something, particularly a commutative star algebra. So once you have a commutative algebra that you think is near this situation, then you have a space, the spectrum of that algebra. The algebra is the functions on that. And the fact that you've deformed it a little bit away from commutativity, that's the symplectic structure. The symplectic structure is, we'll come back to that, is a small deformation of the commutativity of algebra. Well, it can be, what do we mean when we say that an algebra is a deformation of a commutative algebra? You see, you really mean that you have a one-parameter family of algebras depending on a small parameter R, which is defined in the neighborhood of the identity. A naught is commutative. And if you identify all these as vector spaces, so that what we have is a single vector space with a one-parameter family of multiplications, varying, starting with a commutative multiplication, then of course what I mean by saying that the Poisson structure is the deformation of commutativity, that says that this is equal to the naught plus something like IH, a Poisson bracket, plus order H squared. And this first order deformation is the Poisson bracket, which is equivalent to giving the symplectic structure. I'll leave that and I'll go in accordance with my policy. So, you see, one of the things I'm emphasizing is that this project is certainly part of non-commutative geometry. We expand our picture of manifolds, symplectic manifolds, to some larger class of non-commutative objects. Now, I want to actually dwell on that just a little bit more, because you see, I'd like to say something about the difference between the classical reason for the existence of the symplectic structure and the quantum reason. You see, from this picture, I've said that the symplectic structure is the residue of the fact that the quantum algebra doesn't commute. But there's a sort of converse to that. Before quantum mechanics was invented, people would have said that the symplectic structure was there for a completely different reason. They would have said the reason why the state space of a mechanical system or physical system is a symplectic manifold is that the trajectories, the evolution of the system, is determined by a variational principle. So let me say just a word about that. So the variational approach, one introduced the paths, one associated the new to this, which is the C infinity maps the trajectories in the configuration space of the system, not necessarily obeying any physical laws. And then one said that there was some action functional. Well, that's a little bit too crude, so I'll be a little bit more precise. Let's actually introduce some part of this. This is the inverse limit of a lot of things like this, where this is subinterval. And these are the maps from AB. So the things that are time interval AB. So on this thing, there will be an action function of SAB with real values. And traditionally, it's meant to be of the following form. So when you have some trajectory, then this is meant to take the form of an integral or some function of a tangent space so this L is a function of a tangent space, which we remember the classical configuration. So it's a particular kind of function. And the variational approach, the principle of least action approach to classical physics, said that Ym should be thought of as the critical trajectories of SAB or SAB. I mean, this space is the inverse limit of all these. So we consider things which on each of these things map to a critical. So let me say that a little bit more precisely. Let's observe that this space of all paths, on this we have two projections. The valuation of time A and the valuation of time B. Now on here, maybe I'll just keep this clear thing going from A to B. That's a little bit clear. Now we have this function. So let's look at its gradient, df of d. And you do the usual calculation of the calculus of variation, and you find that the gradient of this function is a valuation b star of alpha minus the valuation of a star of alpha, plus an integral from a to b of something which you traditionally write as the variational derivative of L with respect to x in t. Where alpha is one form from t out. So that's the usual integration by parts things. You can think of this variational derivative, if you like, as a kind of vertical derivative of SAB. So the whole gradient is the sum of this piece and two one forms pulled from the two ends. Well, you see, the critical part means the part where the variational term vanishes, where the Euler-Lagrange equations are satisfied. So on the critical set, this term goes away, and therefore we have this, d of this is this minus this. And if we take d once again, d squared is 0, so d of this one form equals d of this one form, and that's the symplectic form. So the symplectic form comes precisely from this variational, very general variational way of looking at the description of physics. Now that seems very different from saying something is non-commutative, but actually it isn't so different, because I don't think we'll spend so long on that blackboard, so I'll go back to this one all the same. Because it's a good way of, one of the ways of getting at quantum theory, and indeed the quantum field theory, and one of the most influential, is because of what's called the path integral approach, or various names of that kind. And that comes about the following way. First of all, let me make another remark which takes one in the direction of quantum field theory from quantum theory itself. You see, I spoke about a non-commutative algebra. Well, in fact, we don't use most of this algebra. We have an algebra, and we have this theta, which is like the variator at the point of manifold. All we're actually going to use is for each sequence, finite sequence of different times, r being time, what we're going to use is a sequence of multilinear maps, which take well, also we have the time evolution. So supposing we have this thing and we have its time evolution, which is given by unitary transformations A to A. Unity being automorphisms of style. So supposing we So, in other words, we take these elements of the algebra, we think of them as all initially at time 0, we spread them out at these times by using time evolution, and then we apply this operator. So that's a collection of linear forms, and I claim that that's all we ever want to know out of this algebra. Well, one of the things, if you're not familiar with this, it may be helpful to make the following comment. If you're used to thinking of quantum mechanics in terms of a non-commutative algebra, commutation relations between position and momentum, and so on. So let me say something else first. Well, so the path integral approach to quantum mechanics, which you'll see relates a non-commutative algebra first to this, and then to the variational principle, is to say that we introduce a measure which we write on this whole space of paths, not just the one that obey the evolution. So this is a very vague kind of expression, we just imagine that there's some kind of Lebesgue measure or something on this space of paths, and we weight it by an action functional, where we divide the action by a very small constant, h, Planck's constant. So this is a very rapidly oscillating interval. So this is somehow a measure which by stationary phase is somehow concentrated around the critical points of this. And if we were to introduce a measure like that, we can define a lot of functions like this in the following way. Let's define AT as the ordinary functions, the C infinity functions, Pm to C, which depend such that the value depends only on the infinite jet of the path at time t. So this is a path in the configuration space. Let's consider functions of that path which just depend on where it is and how fast it's moving, how fast it's accelerating and so on at t. So that's a function. Now of course by translating in time, these things are canonically isomorphic for all t. So we can now
You will nothing say about the existence of this method.
sorry?
You will nothing say about the existence of these measures.
Well, not in this
They
lecture.
don't exist.
Sorry?
I think they will not exist.
Okay, right, but that's a big, that's kind of, that's the whole subject, right? I mean, I can't, obviously, I can't give you a proof of the right now, that will be very nice. No, but I want to just talk about the conceptual thing for a moment. Given these things AT, which are all isomorphic to each other, we can define multilinear maps by taking A1 to the integral over Pm of A1 of y, AK of y. Some such formal expression, we can try to define something like this. So if we allow ourselves to say, instead of having a variational principle, we've enlarged the space of classical trajectories to ones that don't obey the equations of motion. Suppose there were some kind of measure on it, then we could write down on these spaces of functions a lot of things like this. And we might hope they would be the things which come from our quantum system. Now, in fact, the complete quantum system would be encoded in that. You see, if you give all of these forms, then of course they mightn't come from a multiplication in the algebra together with a linear form. But if they did, they would come essentially uniquely. Now, that's not quite a precise statement, in that if we're talking about the classical picture where we have a symplectic manifold Y and a point in it, and a flow on that, then of course we could always replace Y by some symplectic submanifold which was closed under the flow and contained the point Y, because anything out of that wouldn't really be describing the world at all. Similarly, this describes all we're ever going to use as the output. Now, so quantum field theory is a slightly hybrid thing. I first told you it's going to consist of a functor which is going to associate to a manifold a quantum system, and then it's going to do quantum mechanics. But it's actually also going to suggest a slightly different point of view on quantum theory itself, in that it's going to suggest that maybe an algebra isn't quite the right thing, and all we're actually going to use out of it is this structure. And that is going to become more and more central. Now, people, of course, have thought this thought quite independently of the line I'm taking at the moment, because of the observation that if this is how the quantum theory describes the world, a non-commutative algebra, then you would expect the multiplication in the algebra to correspond to some natural physical operation in the world. And of course that is not the case. The commutator of two elements of the algebra plays a sort of physical role, and some other things do. But the multiplication in the algebra itself doesn't have any straightforward physical interpretation. The remark I was going to make before, if you're not used to this thing and you want to see how the path integral picture is connected with the usual commutation relations which you know, I think the essential thing to keep in your mind is that supposing, for instance, we were considering a particle moving in a manifold. Sorry, I put my glasses, I can't see it. What time is it? Right. Supposing we were considering a free particle moving in a Riemannian manifold just without, not under any forces. So we know classically it will move along a geodesic. Now the measure which will, on the space of paths, which would be associated to this system in the way that I've described, is so-called Wiener measure, random walks on the manifold. Now one of the crucial things to keep in mind about this measure on the space of paths is that when you have a Brownian path, a random walk, then in time t, the distance it goes is, roughly speaking, like the square root of t. It's not like a bullet which goes a distance proportional to t in time t. It goes something like the square root of t in time t. And that's precisely, this measure is precisely encoding the commutativity. So for example, supposing you had a particle supposing you had a particle moving along the line. See, so supposing you wanted to work out its velocity at the origin, how would you do that? Well, you look at where it was at time t, look at where it was at time 0 and divide by t. So that small t is an approximation to the velocity presumably at time half t. Supposing we do that, and then, so this is a function of a path x. Supposing we look at where it is at time x. On the other hand, supposing we do the same thing but we looked at its velocity at time 0. So at the beginning of the run instead of at the end of the run over which you measure the velocity. Supposing we take the difference between these two things and we take the expected value of that. Well, you see that's just the expected value of x of t minus x of 0 or square of t. And that's precisely as t tends to 0, the thing that tends to a constant. In other words, if you measure the velocity and then you measure the position, that differs from measuring the position and then measuring the velocity by something which is roughly speaking a constant. I mean, that's a very schematic description, obviously, but you see how the fact that the distance is proportional to the square of the time is going to encode this failure of velocities and positions. Okay. Well, it's time to get a little bit closer to quantum theory. So, Actually, perhaps let me make one more sort of metaphysical remark. What is the last time I was in Bonn, I gave a lecture something like this, and I got very much attacked, not by people who thought the path integral didn't exist, but by people who thought it worked very well, and they calculated it numerically on their machines, and they got very angry with things. So one gets shot at from both sides. I want to what I want to emphasize is a slightly different point. The thing that is philosophically wrong with the path integral, in the usual way it's stated, is that the paths over which you integrate are paths in some space of classical configurations. Now, once you do that, you're already assuming that you know some classical world. Whereas in quantum field theory, you're trying to find the classical world. So the next thing I want to say is I want to emphasize one of the basic mysteries of quantum field theory, which was already discovered in the 1930s, that the world you're finding in your non-commutative algebra is really rather different from the world you're putting in your field theory. You see, the classical phase space, the symplectic manifold, that was meant to be really there. They were meant to be states of the universe. But the path space we embedded it in, well, they were all the things which were not states of the universe. And that's really very open-ended, and it's not clear how you should describe any such thing. So if you could somehow produce some path integral picture which didn't need you to have a classical picture first, that would be very interesting. And so my approach to the subject, and of course a lot of other people's also, has been to try to somehow formalize, encode, axiomatize what you want out of path integrals without trying to invent path integrals, which, as we just heard, is a very dubious enterprise, and I think the safest thing to say it's only been very partially successful. Many people would say not successful at all. So let me just say this other final metaphysical thing about how what you put in is a bit different from what you take out. You see, one of the mysteries of quantum field theory right from the start was it seemed to be about fields, and yet we see particles. So that's another aspect of the non-commutativity. And again, I'd like to put it right, only very vaguely, but I'd still like to put it right at the beginning in the foreground. So, you see, what we want us to see is supposing, you see, we are going to replace this space P on which the measure is described. Typical kind of situation is to say that this is, let's say, scalar fields, this is a very simple example, on the time interval across a spatial manifold. So C infinity functions on this will say real value. And we can put some action on that. But the system that we're going to see is going to look like the following kind of manifold. It's going to look like a disjoint union for all k. We're going to see particles sitting in here. So we're going to take, that's a symmetric group of using the particles. So this isn't quite a manifold because of problems on the diagonal, so let's not worry about that. So how does this space, or possibly a cotangent space, or the functions like that, have any tendency to look like this? Well, there's a very basic, very well-known theorem, of which I want to point out to you. Supposing on here we introduce some functions of fields defined at a time t. So we say that this is, let's say, let's choose the C infinity function on M, perhaps with compact support, or we can even assume M is compact if you like, and let's consider the following thing. simplify. And this is meant to be integrated over m. This is at particular time t. So we'll fix the time t and we consider this thing. Now this would be the energy density of this scalar field at the point x. And we've taken this smeared out sum of it. We're thinking of that as like a kind of distribution and applying to its test function. Now, you see, the surprising thing is that, well, these, when we make our quantum, this is a quantum linear system in the most obvious sense, and we know a great deal about the elementary quantum mechanics of linear systems. So these things, A, F, for various F, they commute for all F. And because they're quadratic functions, of course, on this vector space of fields. But what happens? The algebra, topological algebra, I should say, they generate.
Sorry, what does commute mean in this context?
Sorry?
What does commute mean? AF is a function that takes a scalar field and puts out a real number.
Sorry. What I meant, sorry, I was jumping ahead. Here we have a linear space of fields. And let's just assume for the moment that we know how to quantize this. And so we're going to say that if we look at functions of the fields at time t, we can promote them to elements of some non-commuting algebra. And this is meant to be the non-commuting algebra. So it's meant to correspond to that classical function. We're going to make it into an algebra by some kind of path integral procedure, which in this very simple case we know all about because it will be a quadratic, it would be a Gaussian integral as well. So we will somehow extract the non-commutative algebra from this, and we know all about that. Now, inside it we have these commuting things which seem to be telling us the distribution of energy in this field as a distribution. Right, we're saying that's what these functions measure. So you would expect that they would tell you that the energy was somehow smeared out in some way. But because of the non-commutativity of the algebra, the algebra they generate is actually isomorphic. So the C infinity functions on xm, that being xm. Right. So this thing, this is just the AFs form something which is a symmetric algebra on the vector space of functions on M. So just algebraically, if there were no relations, they would be like this. But because of the non-commutativity, we see that this algebra gets squashed down into functions on this, where the natural map from this to this is the following. Given a function f and a point in here, x1 to xk, we take f to the function which takes x1 to xk simply to the sum of those things. And then this is the universal commutative algebra, so we extend by the obvious algebraic map. But this is the algebra, the functions on this which exist. Now I claim that's not only true, but it's very simple. And it's essentially the consequence of the Stone-Weierstrass theorem, which is the case when M is a point. You see, suppose you have an element of your non-commutative algebra. So think of it as a self-adjoint operator in Hilbert space. We know that as an operator, it will then generate an algebra of operators which looks like the algebra of functions on its spectrum in the usual sense of an operator in Hilbert space. Well, now supposing we have an operator, and we happen to know that it sits inside an algebra in which it can be factorized as B star, where B and B star are two other operators which don't commute. So supposing they satisfy the commutation relation with that equal to 1. Well, so the fact that this is in a non-commutative topological star integral with this factorization, that immediately implies that the spectrum of A is not the whole real line, but is precisely the natural numbers. In other words, if you think of this as acting on Hilbert space, you can write the Hilbert space as a direct sum, where H0 is the things that are killed by B star, and HB of HK is HK plus 1. Then that's meant to be automatically orthogonal decomposition of the Hilbert space. So that the algebra that A generates looks like the functions on the natural numbers. Now, what happens with these functions? So think of that A as being like this, except that now we have an F and AF with each element F in the vector space. If we say that this sits inside an algebra, which the things that would correspond to B are simply, a little bit too complicated to explain in this lecture, but I'll explain it later, some combination of these phi and phi dash we can make out of it. Their existence will say that instead of this just being describing some smeared out distribution of energy over the manifold, it will describe a discrete collection of a finite number of particles. I'll say more about that later. I don't have very much more time in this lecture, and I really do want to say something about the formal structure of quantum field theory. So I'll do that now. So one of the things that I've kept away from so far is relativity, in the sense that nowadays, of course, we don't believe that time and space are independent, but they fit together into some space-time manifold. And so the traditional formulation of, so now let's promote M to be space-time. Now, in quantum field theory, we assume space-time is given. In that respect, we're just like physics in, just like classical physics. So traditionally, we said the quantum field theory on M gives a vector space of so-called observables to each, let me give it a name, OX to each X and M. And a multilinear map to each distinct, to each finite sequence of distinct points in M. And all the information is meant to be encoded in that. So that's meant to be, remind you of the way I went from the algebra to the sort of Wiener measure collection of things at various times. But you see, the trouble with this approach is that it's extremely difficult to say what properties such a collection should have. Now, the motivation is the path integral approach, which tells us that what we're trying to think of this, we're trying to think of a ghostly thing in the background. We have a ghostly idea of a space phi m of fields, whatever they may be, on M, is the way that we have scalar fields up there. And Ox is meant to be contained in the C infinity functions on phi m. It's meant to be the functions which depend only on the jet of the field at X. Now, as I haven't told you what the fields are, but they're meant to be some sort of vague things like scalar valued functions or Riemannian metrics or sections of some natural vector bundle or whatever. So these are meant to be some ghostly things on them, and we examine them at various points. Now, remember that I said that the measure had a very particular form. So we want to say that this thing Ox1 cross Oxk C, that's meant to take A1, AK to the integral over this phi m, so in this notional thing, of A1 of y, AK of y, e to the I over h, s of y. So that very ill-defined integral. So that's the thinking behind it. And we'd like to somehow axiomatize this situation so that without introducing any such measure, we can say what we want its formal properties to be. Now, the most salient property of this is that it's meant to be local. You see, the action before, when we integrated the Lagrangian along the path, that clearly was additive with respect to the path. So this S certainly has the following property, that if we the S is meant to be local in the sense that if we write our manifold as a disjoint union of two pieces, well, I'll write it as a union. Let's divide it in the way that one does in measure theory into two disjoint pieces. But of course, all the problem is precisely what happens at the interface when we consider. That if we have a y, then this is additive in the sense that this and that might make one believe that, you see, this measure, E I over H S of y, dy, that was somehow meant to be a product measure, in the sense that we ought to be able to say that phi m was somehow the product of phi m1 plus phi m2, and we might hope that this measure, this measure, is somehow the product of two measures on the two pieces of that situation. Now, if this thing S were simply didn't have any, with the integrals of the Lagrangian which didn't have any derivatives in it, then effectively the different points of the target of y would behave quite independently. The values at different times wouldn't interact. The values of y at different times or at different space-time points are bound together precisely by the differentiations in the action, and they express the non-factorization of this. So the central idea is that in this situation, if we were going to have a measure for m, we aren't, and we divide, now let's think of m as being something like a manifold which we divide into m1 and m2 by some codimension 1 manifold n, then we'd like to say that there's a measure here which is trying to be the product of measures there and there. So we'd like to say there's a measure somehow, somewhere on n. And we'd like to say it is somehow made up of things into two pieces. That's where the locality of physics comes in. And what we shall say is that associated to this situation, there exists a vector space, a topological vector space. So better still, a pair of vectors. A pair of topological vector spaces, V trivial in duality, associated to this submanifold n, and in such a way that one of them corresponds to one orientation of n and the other corresponds to the other orientation of n. So a choice of one of these corresponds to a choice of orientation. And we have a measure with values du and 1 with values in V, let's call it Vn, and another measure du m2 with values in V fiddle with n, such that the measure that we originally wanted, our path integral measure, is a pair of these two things. So the transmission of information from one region of space-time to another happens by the appearance of this topological vector space associated with the membrane, which separates things into two. And the formalization of this is the program which I'm going to be telling you about. So it's already over time, so I should stop for today. I didn't get quite to where I wanted to stop, but we'll go on from there on Wednesday.
Any questions? Right. Well, there's tea and coffee in the room, and